let's just throw some definitions at you from the code world. There are a number of kinds of codes. You can divide them into different characteristics. Some codes are what we call systematic codes. Systematic codes are codes where you can actually read the data right inside of the code. I like to use that for block codes. It's a little easier. Like for instance, suppose the data was 101 and that the redundancy is 00 for this calculation. And that if I have 110, then the parities are some other. I don't know what they are. This is just some code. But the interesting thing is, this is the message. This is the parity. So I can actually read the message right inside. You know, some other code that might not be the case. That I might put in a 101 and what I get out is 011111 or 11. I don't know. This would be a non-systematic code. I can't read the message right in there. But there are other codes which are systematic, which just add things on to the message that's already there. Now, systematic codes and block codes are really convenient because the performance is exactly the same for systematic codes or non-systematic codes, but not true in convolutional codes. Convolutional codes, if I forced myself to have a systematic code, that code would not be as good as others. So systematic code, that's the definition, but we're not going to see them very often in convolutional codes. Cyclical codes are codes where each word is a cyclic rotation of the other. Situations where that might be useful. Catastrophic codes. These are bad things. So that when we're going through the effort of finding good codes, you know, generating codes, trying to come up with calculating a free distance of a code, and trying to find out for a given constraint length, you know, what is the best code I can get? What is the largest free distance I can get? Well, one way you can do this is numerically, and we can look for catastrophic codes, throw those out right away, because what is a catastrophic code? A catastrophic code is one where I have just a few errors in the path, you know, a finite number of errors, countable number of errors, but somehow when I put it through my decoder, it generates an infinite number of errors. Like once I get that many errors, my decoder never resynchronizes. It can never catch back up. So catastrophic codes are catastrophic, and so we avoid those. Vocabulary. So the last thing is a perfect code. A perfect code, remember I said that the number of errors that could be corrected was the greatest integer in. Suppose the greatest integer is exactly into it. We call that a perfect code. Not perfect from the sense of good performance, perfect from the aesthetic beauty. We don't need that greatest integer, it's exactly into it. So just the name of a perfect code, but not a high performance code necessarily. So again, I'll mention that systematic codes could exist. In the case of a systematic code, what would that look like in terms of our encoder implementation? So a systematic code would have one of the code bits, which is exactly no math, right? I just take the input and I make it my output. And then these become my parity bits or my added bits that are added. But like I said, these are less efficient than non-systematic codes for convolutional codes. And there is, for instance, for a given k, you can look through all of the systematic codes and find out what would be the best one and calculate what its distance is. And then you do the same thing when you no longer have the constraint that this has got to be systematic, and you can see that you can get a larger free distance with the non-systematic codes. Now, suppose that I have a given free distance. I know how many bits I can correct in a sequence, right? So that's what the T tells me. But a more useful metric for how strong my code is might be the gain, the coding gain. So what is the coding gain? And I can approximate the coding gain by, it's an upper bound approximation, and it's a very simple equation. So in dB, 10 log 10, it would be the code rate multiplied by the free distance. So here's a rate 1/2 code, and here are different constraint lengths, and people have gone through and studied for this rate, this constraint length, what are all the possible codes, what is the best possible code, this is the best possible free distance for all of those codes, and then this is the gain associated with them. Same thing they did for a rate 1/3 code. Find all the codes, find what best ones. And what's interesting from this upper bound, even if it was not precise, the upper bound is great because it tells us that things are saturating. You know, how much more improvement can I get as I go from complexity? Remember, the number of registers goes up 2 to the k minus 1, so, and the memory requirements and the decoder goes up, so growing exponentially in complexity. And I can see what kind of trade-off I have in terms of the improvement in performance. So for this rate code at least, it's not really paying off much to go to the larger constraints. Certainly from 7 to 8 makes no sense because the gain is going to be pretty much the same. So this is a gain that's possible to be achieved by that constraint length and that free distance. So on the previous slide, we saw a upper bound on the performance of a code based simply on 2 characteristics, the constraint length and the free distance, and of course the rate of the code. Now suppose that we weren't interested in an upper bound, but we wanted to find actually the given gain for a certain bit error rate. So what we would do in that case is we would plot the uncoded bit error rate, and then we would plot for a given code what was the coded bit error rate. And for the coded one, we would pick a level of bit error of performance that we were interested in, 10 to the minus 3, 10 to the minus 5, 10 to the minus 7. And we would see for that value here what was the gain of that code. So in this table, we have looked at different code rates, different constraint lengths, and cuts at different levels. So the upper bound is sort of an asymptotic as we get farther down on the curve how much gain we could achieve. So we can see here for different codes how close they might actually get to this upper bound. So this is one way that you could choose, for instance, the level of coding that you needed, what gain you were looking for in your system, and what kind of constraint length, what kind of compromise. Remember, code rate tells you how much expansion you need in your bandwidth in order to achieve the coding. And here we would get the gain that you'll get in exchange for paying for more spectrum. So another way that we could take a cut at how performance is increasing and the trade-off you're making in terms of complexity and gain is, in this case, to fix the rate. So when I say fix the rate, I mean fix the bandwidth expansion factor. And here we'll take an example where that bandwidth expansion is 1/2. And we're going to take, in this case, we're going to plot the bit error rate after coding versus EB over N0. So we're looking at this coded performance. And we're going to look at how we vary the complexity. And the complexity is determined by the constraint length of the code. So here, if I was going to put the uncoded bit rate, I plotted it here, but I guess I didn't plot it here. It probably goes off somewhere like that, the uncoded one. And now I say, what if I had constraint length 3, constraint length 4, 5, 6, 7, 8, and it would have better and better performance. But of course, I would need more and more registers, and as I got into my decoder, I would need larger memory. There would be a much larger number of states, so more calculations per symbol interval, etc. So the complexity is determined, but we can see the trade-off here, and we could fix the performance at a certain level of service that we were interested in. We could take that cut, and we could see how much gain, additional gain, we can get with each one of that complexity, and we can make our choice on how we wanted to proceed. So I said that there has been a lot of work on convolutional codes to try and find the optimal codes, and it has often been the result of an exhaustive search where you search through all codes, use eliminate catastrophic codes, etc. And there's a large number of codes that are potentially of interest. Here's a table where we have gathered together the solutions that people have found for the best codes. And here is the rate of the code, 1/2, 1/3, etc., and the constraint length. And then the free distance that can be achieved, and this is the code. So here is the vector, which gives us the interconnections used in the shift register implementation for the code. And there's a nice command in MATLAB that just does this. It used to be a big topic of research in '76, but nowadays it's a MATLAB command, and you can give it the vectors for your code and say, well, MATLAB, calculate for me what's the free distance for this code. And then once it has the free distance, you can say, well, how many paths are at that free distance? Remember, we had to go through all the different possibilities of the different paths. Well, there might have been where there were a couple of those which were at the free distance. And so it'll tell you how many paths. And then say, well, what if I had one worse? Or one better, I guess I would say. What about the free distance plus 1? How many paths were that? So that if I was comparing two possible codes and they both had the same free distance, well, I would pick the ones that had fewer paths at the free distance. And if they both had the same free distance and the same number of paths at the free distance, I would keep going like that. And so that would be how I would arrive at, finally, this list, which is the best one, because I had compared them on all of these categories. So in summary, we've seen convolutional codes. We've seen different kinds of convolutional codes. And I just want to say some typical values that you will see. We had hard decisions and soft decisions. Both are very common. Soft decisions, you're not going to see any with more than 3 quantization bits. It's just not worth it. We look at constraint lengths. If we go beyond k = 9, really the exponential growth, it just gets too big even for VLSI. And so we're typically looking at k somewhere between 3 and 9. Code rates, we're almost always above 3 to 1. And the maximum path, like I said, and the traceback length will typically something below 5 times k, because beyond that it's just not a good trade-off on the memory. Chapter 8 of the textbook covers some more advanced topics in coding, and of course coding is a huge topic. And there's all kinds of codes that have really come to the fore. More recently, it's constantly improving, although pretty good right now, but you never know when another breakthrough is going to be coming through on the complexity and the way of implementation or decoding. Reed-Solomon codes, very, very popular codes. These are cyclic codes. They're not binary. They're based on symbols. And they have very good free distance properties. They're especially good at bursty noise. So when you are likely to, when one thing goes wrong, maybe a bunch of neighbors goes wrong too. So in a channel where the noise is not necessarily Gaussian, but some other, and it could be sporadic emissions that are, bursty in nature. And because we're looking at the characteristics of this code make it very robust against that, because when it corrects errors, it corrects all neighboring errors at the same time, so this is very good. We also see interleaving as an operation which helps the efficiency of codes. Concatenated codes, really important, taking 2 codes and combining them together. So first we have an inner code, and then we have an outer code, and there's different kinds of doing the decoding. Either we completely decode the inner and then the outer, or we trade messages between them and iterate between them. That's usually the best way. So we can get very good performance. Turbo codes, decoding that is, like I said, you can go back and forth between the different kinds of decoding operations. It's very good. So you're welcome to cover these topics. We just don't have time to do it all, and it's probably another class you could take in error-correcting codings that would address this. And LDPC codes are not even covered in the book. A very important topic, probably came out after the book was really popularized. So we've only touched the surface of codes, but the important part is that you have an appreciation for this exchange between spectral efficiency and also the complexity in order to increase the bit error rate performance.